Okay, so let's go over section 3.5, and we're going to learn how to solve exponential and logarithmic applications. We'll look at some of the applications in lab. Okay, so first thing we're going to do is just go through exponential equations, and then we'll look at solving logarithmic equations. Okay, so what does an exponential equation look like? So in this case, the variable that we're going to be trying to solve for is going to be in the exponent. So we know how to do things like 2x plus 1 is equal to 5. We know how to solve this thing, get rid of all of this. Get that over on that side. Get rid of our multiplications, and then that solves it. But now we're going to be looking at things like now the variable is in the exponent, okay? And I want to know when that, well, this one we can kind of look at, well, this is just 2 squared, right? So x is equal to 2. 2 squared is equal to 4. Okay, but it's not always going to be that simple. Sometimes we're going to have to do logs. Sometimes we can do kind of this, is saying, okay, well, isn't 4 the very same thing as 2 squared? So that x must be equal to 2. Here's my base. Here's my base. So if I can get something to be like b to the x is the same thing as b to the y, then x must be equal to y. These numbers must be the same. That's what this is saying. Okay. So anytime I can get some exponential equation to the same base, then I know the exponents are equal. These things are 1 to 1. There's not going to be 2 values that gives us the very same thing. Okay. What about if I have something like 2 to the x is equal to 7? Then I know I can basically now, once we've gone through our work last week, is to say I can represent this as power of any base. Okay, I want to represent this number as a power of 2. What is it? It is the log base 2 of 7. Okay, and now we basically got this. This must be equal to that. Okay. All right, so let's kind of continue on. So here, solve this. And if I didn't have my, calculator to do log tables or anything, I'm looking to see if I can get both of these to the same base. Well, 4 and 8, this is not a power of this, but how about 2? 2 squared is 4, 2 cubed is 8, but this isn't, I want the base 2. This would be 2, this would be negative 2, right? 2 to the negative 2, so 1/4 is 1 over 2 squared. I kind of got this side, comma, 8 to the x is what I'm solving. Well, this is just 2 cubed to the x. I've got this is 2 to the negative 2. Now that I've got some same bases, this is what I've got. 2 to the negative 2, 2 cubed to the x, and now I've got an exponent raised to an exponent. I just multiply the exponents. So 2 to the negative 2 is equal to 2 to the 3x. That would be 8 to the x power, okay? So now I'm just going to solve. My bases are the same. That must be the same exponents. And I solve just like I would a linear equation. So my x is equal to negative 2/3. So let's do something very similar to this one. I would like to solve 8 to the x plus 3 power. When is that equal to 4 to the 5 minus 2x power? And I want to get these to the same base is what I'm looking for. Okay, so here I had 2 cubed x plus 3, I put that in parentheses, 4, which is 2 squared, and now I'm going to do the very same thing. I multiply exponents. 2 to the 3 times x plus 3 is equal to 2 to the 2 times 5 minus 2x. And now my bases are the same, so this has got to be the same. It's a one-to-one function. I should be able to only have one value that's going to give me this. So that means 3 to the x, 3 times x plus 3 is 2, 5 minus 2x. And then I just distribute, group, and solve. So 3x plus 9 is equal to 10 minus 4x, distribute. Get all my x's over on one side, so plus 4x, plus 4x. 7x plus 9 is equal to 10. Minus 9 on both sides to get rid of that. 7x is equal to 1. And then x is equal to 1/7. And then we should go back and check and make sure. So I want to do the very same thing. I want to solve this. 3 to the negative 0.02x is equal to 0.07. I could do the base 3, but I'm going to go ahead and solve it like I would normally do. I don't care. All I'm doing is looking for x. I can pick, and the easiest one to do is take the natural log of both sides. Okay. I'm representing both of these numbers as a power of e. These are the exponents. So the exponent should be equal. That's why I get this is equal to this. If this is equal to this, a log of this is equal to the log of this. I can do it with either log, common log, any base. If I did the base 3, the same. But this is what's going to happen next. The exponent comes down here. So this is now minus 0.02x. Natural log of 3. I keep this. And now I just want to divide this out. So divide both sides by negative 0.02 times ln of 3. I'm dividing, and then I'm dividing again, or both at the same time. Minus 0.02 times ln of 3. This goes out, so x is equal to the negative log, the log, ln of this, divided by the natural log. Let me put the minus 0.02 times ln of 3. And then that should be 121.03, 02814, rounded to 121.03. Okay, and you may need to make sure that you do all of that. Okay, so if I do 3 to the negative 0.02 times the 121.03, negative 0.02 times my x, does that equal to 0.07? It's probably going to be pretty close. Okay, so I've got 3 raised to the negative 0.02 times 121.08. I get this is 0.06992, and that's pretty close to 0.07 to 2 decimal places, or 3 decimals. 0.07 2 decimals. Okay, so let me go back through, and basically whenever I have, so if I have something, let's just go 5 to the x is equal to 1277, okay? I can do a couple of different ways, but here's all the same thing. So if I want to use to the base 5, $12.77, my exponent goes out front, and now this goes away. Log 5 base and the number's the same. This is just 1. Right? 5 to the 1 is equal to 5. So this gets rid of this, and that's directly. I just go with this. Most calculators don't have base 5 that you can do. T84 you can kind of switch out with a change of base. 36s you can do. TI-30 you can't do. So you need to do this as a change of base. Okay, so what I would do is instead of doing it that way, I would take, let's go the log, base 10, 5 to the x. I take the log of both sides, same base, and I do the very same thing, x out front. And then I solve for x. This is the very same thing that we would get before with the change of base from 10. Okay. What about if I'd have done an ln? X comes out front. Divide by the ln of 5. And that gives me the value of x. This is just the change of base using the ln. It's the very same thing. That's what the change of base does. Okay, so I wouldn't worry about the base so much. I just have some exponential that I need to solve for. Anytime I've got something as an exponential, I take a log. ln is nice because it's just, it's very quick to write. Just ln and script, and then go down and solve it. So I'm going to do that again for this one. 5 to the x is equal to 83. I'm just going to take the natural log of both sides and solve for x, but that power property gets me down, and that's why I want to do the log of both sides. It turns an exponential into a linear function. I'm solving for x, so I want to divide out ln of 5. And if I do this on my calculator, ln of 83 divided by the natural log of 5, I get x is equal to 2.7455804, okay? And if I do 5 to this power, so check 5 to the 2.7455804, and if I do this on the calculator, am I really close to 83? I get 83.000 ... okay, which is very close to 83. I just need to go out these more decimal places to get it as close as what I want to 83. I may not ever actually equal to 83, but I can get it as close as I want to 83 by taking this out to more decimal places. And that's pretty close. So now this gets a little more complicated, but we're going to do the very same thing. We just have to set it up into the right. Okay, so I want to go to all the way to the point that I have just basically e to some expression. Some expression is equal to some number, and then I'm going to take the log of both sides, and that'll give it to me. Some expression in x. Maybe I just said so expression. Okay. So 4 plus 3e to the 2x is equal to 11. And what I want is just e to some number. E to some value, some expression is equal to a number that I take the natural log of both sides, get that 2x out front, and just solve for x, because I want to know what x, not 2x. Okay, so the first thing I want to do, I want to focus on this, really, this part of it. But to get that, I need to take off the outside first. So 3e to the 2x is going to be 11 minus 4, 7. And then I'm going to divide out the 3. This is 2x. Get this cleaned up a little bit. Okay, and once I get this, anytime I'm dealing with these, I always want to use the ln, the corresponding ln. 7/3. This goes out front. The reason why I said I want to always use the ln for e is because this will eventually come down to ln of e. This is base e. That's the log base e. We just shorten this to ln. This is just 1. The natural log of e is just 1. So this piece of it is equal to 1. So 2x times 1 is 2x, ln of 7/3, divide that by 2. And here I can expand ln of 7 minus the ln of 3, but we can do 7/3 just as well. We just need this thing to be in a ln. So I'm going to do ln 7 divided by 3 7 divided by 3, close my parentheses, divide by 2, and I get 0.65. Okay. I'm going to go all the way back up to here, and then I'm just going to check this. 4 plus E3, 3 times E to the 2 times the 0.42365. Does that equal 211? Our original problem. And if I do 4 plus 3 times my E, my E to the X, second E to the X, 2 times that number. And if I do that, I actually get 11, but this takes 0.42365 or 64893 is what I've carried this out to, and I had rounded that to 5. Okay. Okay, so let's kind of continue on. Here again, if I take the ln of both sides, so this is really where it kind of, 3 to the 2x plus 1. Okay. As long as I can show up with both of these things being in the exponential and being in the exponent, I don't care about these bases because I can convert to any base. And again, take the natural log of both sides. That gets me exponents down, okay? If I have plus something over here, I can't do this. Okay, so if I had plus 2 here, I can't do it because I can't isolate a plus. If I've got multiplications, I can do the logs. But if I had plus 2, I can't get this thing isolated, and I would have to do something kind of different over here, okay? Okay, so pick any log. Let's do the common log this time. It's going to be the very same thing. 2 to 3x minus 2 is equal to log 3 2x plus 1. If this is equal to this, then the log of this should be equal to log of this. I'm representing this as this number to a power of 10. What is it? That's that log. Same thing. This to the base 10, and those exponents should be equal. Okay. But this, I need to bring out in front. 3x minus 2 log 2 is equal to 2x. This is the very same thing. All of this, I need to put this in parentheses, not just write 2x plus 1 times log of 3, because that just represents 2x plus 1 times the log of 3. It's 2x plus 1 all times the log of 3. Okay. The reason I want to do this one is because here's a 2x plus 1. Let me make sure that looks like a parentheses on the screen. For me to solve this, I've got to distribute everything out. It distributes among both of these things. And then I got to get all my x's over on one side. So let me show you this. 3x, this distributed here, 3x times log of 2 minus 2 log 2. That's my left side. And then 2x log 3 plus log 3 from the 1. Okay, so that's why you just don't want to draw it 2x plus 1 times the log of 3, because then you just get 2x plus the log of 3. Both of these have the log 3 expression. Now, I've got x is here multiplied, x is here multiplied. I could actually multiply these two numbers to get a number. Here's 3 times the log of 2 is a number, and then work those together. But anyway, I want to get all my x's on one side. 3x log 2 minus, because I'm subtracting this off from both sides. Minus 2x log 3. Okay, so minus 2x log 3. These aren't the same number, but that's okay. Add this, get this over here, 2 log 2 plus log 3. Add plus 2 log 2 plus 2 log 2. That goes out, okay? And now this is what I want to do here. You can do, if you were just running through some quick numbers, you can go 3 times the log of 2, which is just a number, minus 2 times the log of 3, which is just a number, and that would be the x. But for a closed form, I want to factor out the 2. And when I say closed form, I want to leave everything to whatever decimal places we need. So I want to factor out an x. Okay, this is just rewriting. So now I've got this in a multiplication. Now I can divide out this. So I'm going to divide this by both sides. It's going to cancel over here. Parentheses 2 log 3. Sorry, 2 log 2. Plus log 3. That's the top. And then I divide it out here, 3 log 2 minus 2 log 3. Okay, I could bring these back in together, but when I'm calculating, that's good enough for calculation. 2 times the log of 2, that's calculator, plus the log of 3, then divide by 3 times log 2 minus 2 log 3. And if I do that, I would get to log 2 plus log 3 log 2 minus 2 log 3. And then I would get this being negative 21.097. I could bring all of these back together, but it just saves me some extra steps. Just, more writing. There's more to write, but there's less kind of working these things back together. Okay. So work on that. Make sure that you can get this on your calculators to get this value. Okay, so we'll work some more of these. How about if we get something like this? I get a quadratic form. You remember the quadratic forms are something that looks like a quadratic equations, even though it's not clearly, right? So if I do, I'm looking for something, ax squared plus bx plus c. That's my quadratic, right? Okay. This, they want to solve e to the 2x minus 8e to the x plus 12 equal to 0 solve. Okay. This does not look like this, but it does look like something squared. And what I want to do is say, well, the standard is just let you'll see lots of times later on that this u kind of do a substitution type things. If I let u equal e to the x, and then if I squared this is just e to the 2x, okay, which is what we've got. U is that, u squared is this, so this is really u squared minus 8u plus 12. There's my u. Here's this. Now I can solve this piece, and then I just have to remember, well, I've got to go back and solve this, okay? So 2 factors of 12 that add up to be 8. That looks like a 2 and a 6. There's only 2, 6. 12, 1 is 13. 3 to 4 is 7. 2 and a 6 gives me the 8. So this is u minus 2, u minus 6 because of the negative. U squared minus 6u minus 2u is the minus 8u, and then a negative 2 times the negative 6 is my plus 12. Okay? U minus 2 is equal to 0. The only way these two things are going to be equal to 0 if either one of these is equal to 0. So u is equal to 2 or u is equal to 6. But now I got to remember that u was e to the x. So e to the x is equal to 2 or e to the x is equal to 6. And that means x is equal to ln of 2. Take the ln of both sides. X ln of e is just 1. Or the equivalent form, right? Do the log form. X is equal to ln of 2 or x is equal to the ln of 6. So either one of these would work for x. Okay. Same thing here. I'm going to let you work this on your own. Try to get this, ask me in class. Solving logarithmic equations. So let's move on. We're going to go to logarithmic equation. Logarithms is logarithmic equation is where the variable is going to be that. So no longer did we have exponential. I come out to have like ln of 2 is equal to x. This is the exponent is in the log, okay? Totally different question, okay? But there's going to be a couple ways that we can solve logarithmic equations. So let's kind of do this thing, okay? So if I've got, look at the top, the log of 3x minus 4 minus the log x plus 1 is equal to the log of 2. And this one, I've got the log of x plus 6 minus the log of 3x minus 2 is equal to 2, a whole number. And here's 3. Okay, so the way that I solve these two are going to take a different method, okay? That 2 with this log 3, I want to re-represent that as a power of 3, okay? So let's kind of work on these things together, okay? And I'll go through here. You can kind of go back through here. So here is the first method, okay? Method 1, logs, solving logs, okay? So here's what I want to write down first. Here's what I'm going to solve, and then I want to make a general observation. Okay, here's some number I wanted to represent as a base 2. What was it? What is it? That's the log 2. Here's the log. But generally, if A is equal to B, then a log to any base of A is going to be the log base B. Okay, if I take the log of any base, these things are going to be, this is just the exponent represented a as a power of b, is going to be the very same. These are 1, 2, 1s. We only have one number, and if these things are equal, that number is going to be the very same. Okay? So I'm going to use this in reverse. If the log of a is equal to the log of b, then a is equal to b. If I can get this expression, so I've got the same base, they're all together, one log is equal to one log, then 5x minus 1 must be equal to 2x plus 17. If a log of something is equal to the log of something else, these must be equal. So I can remove the log, I don't have to worry about them. I just solve this. And then how do I do it? All the x's on one side, all the numbers on the other side, and then divide out whatever we've got, okay? So minus 2x, let's do the x's on one side. 3x minus 1 is equal to 17. Plus 1 to get that over there. Divide by 3. So our x would be equal to 6. 30, the log of 30 minus 1, which is 29. 2 times x is 12 plus 17 is 29. The log base 2 of 29 is simply equal to the log 2, 29. So again, same method. If the log of this is equal to the log of that, again, log A is equal to the log of B. Same bases, any base, this happens to be 10, then A is equal to B. Doesn't matter. As long as the bases are the same, the log is going to be the same. So this, I just say, is equal to this. X is on one side, numbers on the other. 2x plus x plus x plus 7 divide by 2, 12 divided by 2 is 6. Okay. So let's check it. The log of 6 minus 7, does that equal to the log of 5 minus 6? Yes, but I can't do the log. I can't do the log of negative 1. So this has no solution. If it had a solution, it would be 6, but this has to be greater than 0, and it's negative 1. So no solution on that particular one. If this had a solution, it would be 6. Okay, 6 minus 7, negative 1 would be negative 1, but I can't do the log of negative 1. So during check, doesn't check. So no solution on that. Same thing here, I just say this is equal to this because of the log is equal to the log. That's got to be equal, 7x minus 4 has got to be equal to 2x plus 1, and then I solve just like I did, okay? Now here's a little different. So I've taken it up one notch. We're going to do the very same thing, but I need to do some extra work. I see a logs on one side, logs on the other. I want to bring these logs back in and then solve. So I've got the log 3x minus 4 minus the log x plus 1. That's equal to the log of 2. Okay? I want to put this, method 1 says I've got to have a log A equal to the log of B. Okay, this is 2 logs, but I can bring these back in together. Okay, so what I want to do, negatives go to division, top minus the bottom. So I'm using my last week's scales to rewrite this as 1 log. That's equal to the log of 2, the same base. This is understood 10, this is understood 10. So that means this must be equal to that. And then as a review, how do I do this? Clear fractions. Okay, so I want to clear out these denominators. This is over 1. So the LCD is just x plus 1. I'm going to multiply both of these sides by that x plus 1. Okay. This times this, all of that goes out. So 3x minus 4. And now all of this is over 1, so that's divided by 1. I get to drop this 2x plus 2 as I distribute. And then I solve. Minus 2x minus 2x plus 4. And that gives me, okay, 3x minus 18. So I'm just rechecking this. 3 times 6 is 18 minus 4 is 14. That's okay. The log of 6 plus 1 is 7. That's okay. The original, it's not like taking the log of a negative number. That means I can do this. That means that should be okay. Okay. Which is 18 minus 4, 14. Divided by 7 is 2. That's my 2. But I did this original check to make sure that this was greater than 0, this was greater than 0. And if they're greater than 0, I can do this. This works out to be 2. That works out. That's the 2. That's great. Okay. So again, let me work one more real quick of this type. So the ln of x plus 3 plus ln of x is equal to ln of 10. This, I've got 2 ln's. I want to use method 1. I'll tell you what method 2 is in a minute. We got to go through that. So this I can get into 1, ln x plus 3. Oh, sorry. Plus goes to multiplication x plus 3 times x is equal to ln of 10. That means ln of a is equal to ln of b. This must be the same. X times x plus 3 is equal to 10. X squared plus 3x is equal to 10. Quadratic. Quadratics have to be equal to 0. So I have to subtract off or add whatever it is to get that over here. X squared plus 3x positive. I subtract. Two factors of 10. The difference being the 3 has got to be the 5 and the 2. X plus 5, x minus 2. X squared minus 2x plus 5x, and then my minus 10. So x is equal to negative 5, or x is equal to 2. Now again, when I'm solving this thing, I want to check this thing. If I do negative 5, x plus negative 5 plus 3 is a negative 2. That's not going to work in this case or that case. The x equal to 2, 5, 2, those are both greater than 0. And then this is okay once we do this. 5 times 2 is 10. That gives me the 10. That's going to work. Okay. So that's method one. Method one, in summary, is that I eventually get down to log of any base of some expression A is equal to the log at that same base of B. If I get this down, then A equal to B and solve. Okay? That's method one. Okay. So now method two. Okay, method two says I want to get some expression eventually to one expression. I want to recombine everything. Any base B of something, some expression A, blah, 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 is equal to a number. Let me do a number. Okay, so what does that mean? That means B to the X is equal to A. This is just going to be some number, so this isn't a variable. Let me put this as some number. B to the N is going to be equal to that A. Okay, so this is just going to be an exponential number. That's going to be the expression that I have to solve. Okay, but that's kind of the basics that we're going to go through. Okay, so let's work a couple of these. So this is method two. I recognize method two because I have a number over here, not another log expression. Log 5 of this is equal to log 5 of that. I do it together. Okay. So then I can go to the other piece. This is basically, I'm using the equivalent from the log form to the exponential form. And this is what converting, remember when we were converting, I wanted to represent some number as some power of 5. What is that number? That was 2. That's from the definition. And that equivalence, okay? So they're inverse statements of each other. So now this is what I'm solving. 5 times 5 is 25. Okay, so 3x minus 1, and then divide by 3. 3 8s are 24, so that would be the 8. Okay. 3 times 8 is 24 plus 1 is 25. This is 5 squared. That should be the very same thing. Okay. So that is method 2. I just have to remember to this, when I remove this, this is that power, okay? And I can think of this doing the very same thing as saying working backwards. What did the 2 be? The 2, I can get a log on this side by multiplying. If I do log 5 of 5, this is just multiplying this side by 1, right? And then we go backwards. And then we're back to method 1, okay? But this goes up here as an exponent, and then 3x plus 1 is equal to 5 squared, which is 25. And then again, x was equal to what? 4. 24 divided by 3, that was 8. Okay. So that's what you want to do with n. I just want to take whatever base, remember to raise that to a power to get this into this equivalent expression, and then I can remove them. So let me do another one. I'm going to leave that up there for just a second. Log 3x plus 6 minus log 3x minus 2 is equal to 2. Always have to be the same basis for me to do this kind of stuff. Now, negatives go to division. So this is what this is. Log 3 x plus 6 x minus 2 is equal to 2. Now, what does this? What's the equivalent? This says that x plus 6 over x minus 2. I wanted to represent this as a power of 3. What's the power? That's the 2. Here's the base. Okay? So that's just equal to my 9. And now I just want to solve this. Clear both sides equal to x minus 2. So I'm going to break this out a little bit here. Go back up into here. Okay. So I'm going to rewrite it. My x plus 6, x minus 2 is equal to 9. So to solve this, I want to clear out my fractions, decimals basically, clear fractions of their decimals. So I'm going to multiply both sides by x minus 2. That goes out. X plus 6. Now distribute, 9x minus 18. Since I like positive x's, I'm just going to subtract x from both sides. 6 is equal to 8x minus 18, and then plus 18. Okay, so 24 is equal to 8x. 3 8s are 24, so this is 3. So my x is equal to 3. Okay, and if I go back over here, this is 9, so I'm okay here. 3 minus 2 is a log of 1, that's 0. And the log of 9 base 3 is 2. So 3 squared is 9, and that works out. I just wanted to check again that this was positive on both sides. That makes it a solution, okay? And as long as we check, and that we did kind of a walkthrough. Okay, so let's go with a variation on the theme. Log x plus 15 is equal to minus log x. Okay, which doesn't fit either one of the forms, but what I'm going to do is get it into that form. I'm going to get all of my logs over on one side, my numbers over on the other. So to get this to happen, I'm going to do plus log x to both sides. I'm going to do that to get rid of that. Okay, so log x plus 15 plus log of x is equal to 2. Now I'm getting there. Now I've got some number, some log expressions. I'm going to bring these back in. Positives goes to multiplication, so log x plus 15 times x is equal to 2. And now I just want to recall what this means. This is a base 2. Again, I wanted to represent this as a power of 10. What's the power? 2, which says x plus 15 times x was 10 squared, and that's equal to 100. Okay. X squared plus 15x is equal to 100. Minus 100 is equal to 0. 2 factors of 100 gives me 15. This has got to be the 20 and the 5. It's the only thing I can think of. Hopefully it's that easy. X plus 20, sign of the larger factor, x minus 5. X squared minus 5x plus 20x gives me the plus 15x, and then the 20 times the negative 5. So here x is equal to negative 20, or x is equal to 5. The opposite to get that to be equal to 0. Now I check. When I go back up here, that's not going to work. The log of negative 20 is not defined. Okay. So the 5 should work. Both of these are in the domain. And then once I go through, that should be okay.